Thank you for coming. We're going to talk to you about wireless MPC control with our dividing wall pilot column. I am a graduate student at the University of Texas at Austin, employed with the Separations Research Program. And so when we were founded in 1984, it was with the idea of doing industrial research in an academic setting. And so my co-presenters, Thomas Lamp from Eastman Chemical, are one of my sponsors for the dividing wall column. And then Willy and Terry from Emerson are able to help collaborate on this academic project. And so having both Eastman and Emerson as sponsors in an academic setting really allows for this collaboration. And so just a quick agenda of what I'll talk to you about. We'll introduce what a dividing wall column is, some of the challenges with control that we've faced, and how we've done MPC, the control strategy for it. Willy will then talk to you about Predict Pro and how we put the MPC in place, and how we adapted it for wireless implementation or wireless operation. And then for those that attended last year, we were still building the column. And so this year we finally have test results that we can show you and the results and conclusion of the MPC. So what is a dividing wall column? So normal distillation, you have a binary separation, A and B feed, you're able to separate the A and B streams. This is very standard separation for distillations. So then if you have a tertiary separation, how do you do that? So this is an indirect separation, so you can do the split between the A and the B stream, but then you still have a BC stream that needs another column to separate it. And so what a dividing wall column does is you're able to actually separate three components in one dividing wall, or in one column. And here you can see by adding a wall, it separates the feed from the side stream, so you can pull out a side stream product and actually do a three-component separation in one column. And you can see the benefits of this. You only have one column versus two distillation columns, one reboiler, one condenser, versus two reboilers, two condensers. You save energy and capital cost. This configuration is estimated about 30% energy savings over standard distillation techniques. However, there are some control issues that we have. We add additional degrees of freedom by adding a wall, and holding this column steady can be a challenge. And so that's kind of where we've come in at the University of Texas, is we've actually built a pilot dividing wall column here. We actually first started running it back in January. And you can see it's a 6-inch column, about 35 feet tall, 4 different sections of the column with structured packing. And so we're actually able to mirror industrial applications. And so here you kind of see our control strategy. You can think of it more in 4 different sections of how we control it. The standard overhead section with the rectifying section, we're able to use the reflux as one of our variables. The reboiler section at the bottom, those are very standard to the normal distillation operations. But where a dividing wall column gets more confusing is we have a top of the wall section. And so you might think that we're just going to do a 50-50 liquid split or let it fall naturally, but you actually get a better separation by changing this wall split. So we found the optimal to be about 30% on this side and 70% here, but we actually have it set up that this can be a control variable for us. So we have a total trap tray that we can pull the liquid out into a vessel, and with 2 control valves actually make that split. And so we can use this as an operating variable, and Willy will show you some of the results from that. Additionally, our B products, you can think of it as a reflux. So we have a total trap tray here. We pull the liquid out, and we can either take some as a product and then reflux some of the B back. So that's another one of our operating parameters that we use in MPC. And so you can see how we've done that. And noted the valves in blue are wireless capabilities. And we're doing temperature control instead of composition control. Our dividing wall column is outfitted with 24 RTDs that are hooked up to the 848s. So just by having this wireless capabilities, we're able to have a wide range of temperatures to select to be controlled off of. Without this wireless technology, I think we would still be running wires in our pilot column. So why wireless for dividing wall? One, like I said, instrument cost. We are a pilot facility. We run on industrial donations and research. So we try to do things as cheap as possible. We need flexibility. We're constantly changing what projects we're working on. And so by having this wireless capabilities, we're able to quickly change in between projects. Maintenance, again, we're a low run facility. We have 4 full-time staff members. And so we need something as easy as possible to operate just with our lean staff. And with that, I'm going to hand over to Willy.
Yeah, thank you, Bailee. So definitely the major requirement for that column was wireless measurements, wireless instrumentation in general, because research nature of the column allows easy reconfiguration and cost essentially as well, very important. So applying model predictive control should be fit to that wireless measurements and instrumentation. Emerson, as you know, has standard product Delta V Predict Pro. And those very interesting and important features which has this product, easy graphical configuration, fully integrated with database and historian, automated plant testing and model identification, offline simulator for testing, standard operator display, and definitely flexible LP optimizer, which makes altogether scalable, practical, easy to use. Every one of you who may try Predict Pro experience those features. And from that product, what are additional requirements which comes to wireless control? First, basic requirement, like to any control, is really stable operation. That's what we need to realize. Wireless control, definitely scan may be changing in a wide range. We want to achieve insignificant performance change. Definitely, we assume that wireless control may degrade to certain extent performance. That is obvious assumption. Equally important as stable operation is switch over to safe mode in case wireless control might be not transmitting measurement. To solve this problem, we looked on MPC operation, what is principle of that operation, and what is basic here. I don't go now into detail. That MPC works based on the model. Model is, here is the name CV prediction. Normally, model is developed during the process identification, and model is updated based on input measurements, which goes to the process and goes to the model. As well, disturbance variable go to the process and go to the model. What is important as well, one factor is correction of the model based on real measurements. And those real measurements, in our case, should be wireless measurements. So looking on that diagram, we're coming to a simple conclusion that in case we cut this wireless measurement, so MPC operation will be just based on the model. And this is kind of a nice first conclusion. This is math which we don't go into detail, which supports for someone who may read later and might want to explore details. So now we're coming to assumptions or principle of design of wireless MPC. So first, what we stated already, the MPC in operation uses internal model, which we have. What we need to do that in case we don't have updated measurement, we don't need to apply prediction correction, because measurement what we got from wireless may stay long time as a constant value. We cannot update changing prediction on the model output here. As well as disturbances, if they are wireless, in our case they are, so we don't need to apply same principle. We need to retain the last measurement for disturbances. And that's about what it is. Let's go see how we implemented that design. Maybe before yet, we see on a diagram which explains in what is internally happening in that predictor. First is process prediction shown here. Let's assume this kind of a little bit complex prediction. And normal what happened in MPC controller, there are 3 steps model update. First is time update, so we just shifting time 1 scan to the left and we got updated time. Second, we update effect and MV change, those manipulated variable and disturbances, and that is moving up. It's the result of all those step responses which are implemented at that scan. And what we doing in the third step is the correction of the model prediction based on real measurement, step 3, here in red dashed line. Just again, looking on that diagram, what our risk here in case wireless measurement is not coming, we are not making this correction of the prediction. It's really not significant risk, so we may say that MPC may work based on just uncorrected process output in case we not getting wireless measurement. Another feature what we kind of realized at that time, and definitely we knew of those features, that essentially that principle is applied already in MPC. When one of those features which we have in Predict Pro, that when measurement fails and MPC can work certain period of time, we pre-program that period of time based on model. And that is exactly what MPC fails, and what it means that measurement status is bad. And at that time, when measurement is failed, MPC works based on prediction until it exceeds that pre-programmed time. We usually set in time to steady state, so-called. So then definitely MPC should switch mode to manual or local. That's exactly safe procedure what was another requirement for wireless MPC control. Another feature which is used in MPC is lab data input. So again, it's same principle, which I don't repeat here, that we are taking lab measurements maybe in 1 hour or whatever number of period of time. Definitely this period of time is much longer than MPC scan. So number of scans MPC should work with no measurement, essentially. Lab measurements are available only at those longer time periods. In between lab measurement, MPC works based on model prediction. And what is interesting here, that when there is no lab measurement available, analog input status is constant at that period. And that's what we accept for our wireless control. So we say, let's use similar principle. When wireless measurement is not available, status is constant. When new measurement is coming, status is good. So in general, that MPC may be very easy adopted to that wireless control. This is coding which generate this status of measurement, as we discussed before. It's easy to implement. And those are settings which we use for wireless control. There are same settings as for lab measurements. Namely, we define what will be mode when wireless measurement fail. In that case, you see simulate, fail, shed local. It means that simulate operation based on model, but in fail, then shed to local after a certain period of time. And additional parameter which is not shown here, I mentioned already that we may set time when MPC operate based on model. In Predict Pro, such parameter is sim time factor. It's expressed in multiple of time to steady states. In our case, time to steady state is 120 scans. It's really quite significant period of time, and normally wireless control is available in much less time, like 10 or 20 scans, MPC scans.
What is the range of that sim time factor? Like if we're going from 05 to 10? Or?
No. That's 10, maybe not. As far as I recall, maybe 3 time to steady state, because it's really 2 time to steady states. Let's say real process like time to steady states 1 hour or 2 hours. So it works without measurement, let's say 2 hours or 3 hours. You need to decide what is safe to work.
What's the lowest it can be set to?
Lowest, definitely, you may say fraction of that. So 0.1, let's say few MPC scans. And less than 1 scan doesn't make sense to set, because it's, you want to say how many scans after you get your bad status or constant status you need to simulate. So that's what I discussed already, how we're setting that status wireless control. It's exactly similar or same like for lab measurement. Operator screen has timer here embedded. If we set this wireless mode of operation for any input, and this timer when we work online shows how much time left until it go to local mode or whatever fail mode we define. So in that case, I think we set 2 minutes and to count down until 0 and it goes to fail mode. We tested prior to application on distillation column, we tested in simulation, and what we see here, that this is really top temperature. We developed simplified simulator of DWC. This is wireless measurement of top temperature, and you see just stepwise. Our response of manipulated variable of MPC is very smooth and fluent, because we are not taking those values from measurement. We are just taking only at the points where the new measurement is coming and update our model. The rest of the time, MPC is working on models, so you got smooth MPC operation here, despite measurement, as you see, quite stepwise. And that is shown really that simulated value of the process output, and you clearly see that at certain points are small bumps. That's exactly what happened process model update. As you may recall that diagram when I showed how model is update graphical, so those are shift of the process output trajectory. Another test which we performed was MPC performance. As you recall those requirements, we want that MPC would not lose performance significantly when we work in wireless. And that's what we see here, that those in what we use, integrated absolute error. So that was upper temperature was 126 was wired control. With wireless control and period 8 seconds, it means we use measurement every 6 MPC scans. The performance was not that much worse, and even 16 seconds it still performed well. We need to understand though that this is in simulation. The disturbances were not significant, so operation on model was quite nice, and the drop of performance was not more than 10%. So we went to the process, and use nice feature of automated test of the process. What we done, I have to admit, that we made time to steady state a little bit shorter than we expected. Choose like 20 minutes. We may choose half an hour, but what was the problem here? That this is research column, and definitely there are some other issues to solve in research, some other parameters to explore, and MPC operation was one of the items of the program. So we have limited access of the time. And this is testing. We change feed manually. You see feed flow manually, few bumps. And after 2 or about 3 hours, collecting data, definitely what is standard procedure. And we surprisingly even quite good model, which is shown here, step responses for the process. And what I mentioned about this time to steady state, as you see, some step response in kind of a little bit cut. It might be not coming to completely to the steady state. Those are shown better on this slide. This is model verification. Model was not perfect, but I think this is what top temperature, this is pre-frac, so was really acceptable. We generated controller and put on line operation. What is important, one factor here, to keep all 4 temperatures here, and those are shown here. During operation, we were able to keep more than 1%, maybe was insignificant period of time when exceeded. So when we see here on the temperature, bottom temperature was like 0.2 degree, and the top temperature was as well nearly on the point. So temperatures was kept really very steady. Here on the screen we showed what measurement was wired, was wireless, and overall just typical display for control operation. We made bump during MPC operation feed. There was 10% reduction in feed, trying to see how MPC performs, and that's our model. As you may see now, there were no significant changes in temperature trending here. On some trends, we observed those bumps, which are really express those wireless operation. Why, I may just ask question why we don't observe here, because apparently changes of the measured variable was faster, and then wireless transmission happen when it changes are. And those are results which from, let's say, process engineer standpoint, Bailee will provide.
So as I said before, we have 24 different temperature points on our distillation column. And so this is a graph. This is just in PID control, so not model predictive. We needed a baseline to compare the results from model predictive. And just you can see this is when we implemented PID, so it took a little while to adjust. We also have a boiler that went down twice during operation. It is research, so we take what we can get. But you can see just with the PID, our temperatures did come back. All of these temperatures are wireless measurements. It's steady. My project really is looking at steady state and building a model, so I need very steady results. And so it is steady. So we implemented MPC. This was our first model. It is sort of steady. You can see the temperatures at the top of the column. But we made a few changes in the model. And so the results, I mean, just speak for themselves of how much steadier they are compared to the PID. And so these are the temperatures, again, across the column, and then our MPC model. And so this, to me, just screams steady state. We reach steady state. I can change conditions. You can see we're a little bit of the feed change right here, but it settled out pretty significantly here, and then we shut down the column. And so how does this translate into our compositions? So we take samples every about 2 hours or 3 hours. On the left side is our PID. This is the top of the wall where I talked about we can control the split. We can also take a sample there. And this really composition fluctuates the most out of all of the samples. And so you can see with the MPC, it was much more steady than with the PID control. So our samples really held steady state, which means that I can actually use this in verifying with the model. Again, our side products, much steadier with MPC than with PID control. So this is how we like to operate going forward, is this MPC steady state. And again, the bottoms product, very steady with MPC. So in summary, we were able to achieve wireless MPC. We actually prefer to use MPC over PID while operating the pilot column. Wireless performed excellently. You can see the stable temperatures with the wireless MPC. And Predict Pro was able to help us. Since this was a hydrocarbon system we used in the May. Recently we did an alcohol system and we did the same test, and so we were able to get a great MPC model for a different system. So we've been very happy with the results on our distillation column. And just here's our promo for other wireless presentations that you might want to see. This afternoon we're doing control with wireless. Terry will be on that one as well. We're presenting this one if you just want to get more of wireless MPC at 3:15. There's also another wireless distillation control tomorrow at 8 a.m. and Thursday at 2:15. And then just also on our UT Pilot Plant, we have 2 other presentations using analytics for valve performance. You can catch that one at 10 a.m. today. And then we also had predictive analytics for inferred measurements. So that's this afternoon as well as Thursday. And so with this partnership at Emerson, we're able to use a lot of their technology with our pilot plant. And so here's more areas to get information. And with that, I'd like to acknowledge my sponsors, Eastman Chemical as well as UT, and then Rosemont and Fisher. Without their support, we would not be up and running, and I would not be getting a PhD soon. So with that, I'll take any questions either for myself or Willy.
Question. When you say PID, was that the standard PID or using the PID plus?
PID plus.
So it seems like with wireless, you have a pretty robust model in your MPC. So how was the MPC model verified against process conditions?
So I think I showed model verification, and that was a result you saw that there are plots with real process changes, those are 4 temperatures, and MPC prediction based on model we developed. So there is bias a little bit, and one of the reasons, as I said, might be is we choose a time to steady state a little bit shorter than it truly was because of time constraints of that test was available for process testing.
So Willy, I saw when the wireless temperature is flat, you actually manually use our expression to change the status, is that right? And did you change to 131?
Yes, that's first supposition you made is really true.
Okay.
But 131, is it very constant? 131, I just...
Constant, good.
Yeah, yeah.
And the MPC Pro will no longer use that for updating the prediction, right?
Yeah, when there is status constant, we don't use measurement for updating prediction because in fact, measurement is constant.
Okay.
So when you update prediction, you just mess up with really value, and that's absolutely operation will be not possible.
Sure. So during that period of time, 131, you will see an icon, a clock icon at the operate page saying I'm using the simulated value.
Yes, exactly. Okay. When status is constant, our timer showed up, and it counts how long time you are working based on the model. And we can work only limited time, whatever we define, and after that we go to safe mode, which was our requirement of MPC operation. But it's still, we set that time such long enough that never happened in our case.
So would it have two safe modes? One is you simulate, and then after a certain period of time, shed to the lowest mode?
Local mode, usually I think we set all manual mode, that depending whatever you prefer. Those are two typical safe mode after you exceed that simulation time.
Just a comment on the trends that you have shown for different temperatures. It would be nice to show the variance values for each of them using PID and MPC just for the research.
Yeah, it might be really worth to consider.
So you had analyzers for decomposition?
No, with our volumes, we are not able to do an online analyzer. It's manually collecting samples and running on a GC machine.
So running on a GC machine means you have to batch wise and running through. And composition, one of the control variables, maybe I missed it.
We're doing temperature control based on, yeah.
So you are not controlling the composition as such.
But as I made a note at this point, as you saw composition, trend at the one of those last slides, the composition was very steady. Yeah, so it's kind of correlate temperature, well correlated with composition.
Any other questions? Okay, well, thank you for attending our presentation.